Hello everyone, I'm Zheng Qishu. Today I present my research, The Cognitive Limits of Connectionism using Quantum Associative Memories as the theoretical benchmark. I aim to reflect on the nature and significance of the memory limitation found in the classical biological brain. First, why is this important? Because neuroscience and AI share a common memory wall. Humans are limited by working memory, especially Miller's field chunks, while AI models face catastrophic forgetting. Grounding my work in connectionism and bounded rationality, I ask, can quantum Hopfield networks theoretically break these biological bottlenecks at the algorithmic level? And if so, what does that imply for human cognition? To answer this, I designed a rigorous review. I used the PI-SIL framework to decompose the question into capacity, speed, and robustness. Then, applying the PRISMA protocol, I screened 311 papers. I excluded pure engineering articles and papers with weak relevance, some articles predating 2010 and non-peer-reviewed articles. Finally, narrowed the list to 43 core documents for deep analysis. This ensured the focus remained on cognitive principles and not hardware manufacturing. Crucially, I experienced a research pivot. Initially, I focused on the hardware level, especially NISQ devices. However, I found the physical noise obscured the cognitive principles I wanted to investigate. Therefore, I shifted to the algorithmic level. This pivot allowed me to step outside engineering's constraints and mathematically probe the theoretical upper bounds of memory, which is essential for answering my research question. Moving to the results, I compared the models across 3 dimensions: capacity, speed, and robustness. The quantum model mathematically outperforms the biological models in all 3 metrics. Let's look at the details. First, capacity. Statistical evidence shows biological networks have a linear bottleneck of 0.14n. Overloading this causes crashes, explaining why humans need chunking. In contrast, quantum networks utilize superposition. A network with n units achieves an exponential capacity of 2 to the power of n. Theoretically, this is near infinite storage. Second, speed. Classical retrieval relies on gradient descent, a slow process that gets stuck in local minima. This provides a computational explanation for the tip of the tongue effect. Quantum algorithms, however, use Groover search to implement tunneling. They find the global optimum instantly, simulating a human flash of insight. Finally, robustness. Classical network generates spurious states, mixtures of memories. This is evidence for the constructive nature of false memories. Quantum networks use orthogonality. Mathematically, the interference between memories is 0. This guarantees perfect recall. So what did we learn? The quantum model is stronger, but the brain is not a failure. The quantum model serves as a normative benchmark. Comparing them reveals that human limitations are not bugs, but adaptive features. In a non-quantum world, we sacrifice perfection to achieve generalization and energy efficiency. This confirms Herbert Simon's bounded rationality. We are optimized for survival, not for computation. Thank you.